Hello students, there is another video in matrix structural analysis in finding the nodal displacements of this determinate beam by the matrix approach. So this is just another solution for the lecture part in structural theory. And take note of the answers. This problem is designed and uploaded in my YouTube channel because the allowed calculator can handle 4 simultaneous equations, so therefore 4 unknowns in the analysis. So determine the nodal displacements at A, C, D, and F. E is constant, so we cannot determine this at one time, the displacements at A, C, D, and F, because at A there are 2 unknowns, vertical and rotation. At C also another 2, at D another 2, and at F another 2. So that will make it 8 unknowns. So it cannot be handled by the portable calculator allowed in the licensure exams. So instead we consider B, C, and E first. At B there's only one unknown, the rotation. At C 2, vertical and rotation, and at E rotation. So that makes it 4 unknowns. Now, because we consider B, C, and E, the moment due to this overhang here is 45 times 1 times 0.5, so 22.5 in that sense. The fixed end moment for BC, we imagine that BC is fixed ended. The formula is WL square over 12. So counterclockwise here, clockwise on the other side. So 45 times 4 square over 12 is 60. Then by symmetry, this is also 60. Then the fixed end force is equal to W times L over 2. 45 times 4 over 2 is 90. 90 kilonewtons, excuse me. 90 kilonewtons here, 45 times 4 over 2. Then on the other side for CE, because the moment of inertia is I, for ABC it is 2I. So that's why you have to separate, consider CE. So we have this strip here. The fixed moment is integral of the formula is PAB square over L square, negative at the left. So counterclockwise at the left from slope deflection equation. So integral of differential P, which is 45 dx, A, which is x, distance of the strip from the left, then B, 4 minus x, so 4 minus x square over L square, 4 square. The limits for x is 0 to 2, and that value is 41.25 kilonewton meter. Likewise, the fixed moment EC, which is this, is same integral except that we interchange the factor that is squared. So x is now squared, 4 minus x is just raised to 1 over 4 square, same limit 0 to 2. So 18.75 kilonewton as shown. This fixed end force at E just to the right is obtained by summing up moments about the other end E. So fixed end moment times a fixed end force just to the right at C times 4 FCER times 4 plus 18.75 equals 41.25 plus the moment of the load 45 times 2 meters times 1 plus 2, so 3 meters. So FER equals 73.125 kilonewtons. So the reason why we consider BCE first, because there are 4 unknowns here that can be manageable using your portable calculator. 1 at B, 2 unknowns at C, and 1 at E. So therefore, the net nodal load at D is 22.5 clockwise minus 60. So that would be negative since the fixed forces, fixed moments, and the nodal load are opposite to each other. Therefore, 22.5 minus 60 is negative 37.5. So that means the nodal load should be 37.5 kilonewton meter clockwise. Or in other words, 60 counterclockwise, which is the positive sense of moment with respect to the global or universal sign convention, counterclockwise positive. So 60 minus 22.5 is 37.5 counterclockwise. That's the net fixed end moment at B. And the nodal load would be opposite to that. So that's why we have 37.5 clockwise, opposite to 37.5 kilonewton meter counterclockwise at B. And this 37.5 is negative because it is clockwise. Remember, counterclockwise is positive universally. At node 3, which is C, the vertical load 90 plus FCER 73.125 is 163.125, but the equivalent nodal load should be opposite to that, so it should be downward. That's why we have 163.125 kilonewtons at node 3, which is C, downward. For the moment, 60 minus 41.25, that's positive, so it is clockwise, the net fixed force, but the nodal load should be opposite to that sense. So 60 minus 41.25 is 18.75. The net fixed moment is at C is clockwise, so therefore the nodal load is counterclockwise, 18.75 kilonewtons. And finally at E, which is node 5, the moment 18.75 clockwise minus 48, so negative 29.25, so meaning it is counterclockwise. The net fixed moment at E is counterclockwise. By the way, this 48 here is 24 times 2, and we always do that if we consider up to E only, not considering F. If we consider F, then this 48 is 0 because we imagine that EF is fixed and the load is acting at the fixed support, so it will not contribute any fixed moment, but rather we have reaction of 24 upward, which is equal to the same as 24 downward for the loading at F. But don't mind that first. 48 minus 18.75 is 29.25 counterclockwise, the net fixed moment at E. So the nodal load at E, or node 5, would be opposite to that counterclockwise moment, so it is clockwise 29.25. And this is negative as global force at node 5. So this is the stiffness of BC, 12 EI over L cube. So 12 times 2, because EI is 2 here, divided by, and we treat EI as 1. So 12 times 2 divided by 4 cubed, so 3/8. For students in matrix structural analysis, you should be able to formulate this. I will not explain this anymore because if you are a student in matrix structural analysis, then you can generate these values for the global stiffness matrix of member BC. So that's it. And the numbering is 3, 4, 5, 6 for BC times 2. So this is node 2. So 3, 4, then node 3, 5, 6. So these are the stiffnesses. Then CE, because we consider BCE first. So CE 12 divided by 4 cubed is 3 over 16. 12 times 1 over 4 cubed, 3 over 16. This is 6 times 1 over 4 square, so 3/8. Then the negative of this, then copy 3/8. Then next is 6 over L square, which is this. 4 times EI, 4 times 1 over L, 4. So that's why it's 1. Then this is the negative of this value. This is half of this value. Then this is the negative of the first row. And just review it for you. Then we copy row 2, except that we interchange this 1 and 1/2 here. So 1/2 would be here, 1 should be there. So that is KCE 5, 6, 9, 10. C, this is node 3 and this is node 5. So that's why the numbering is 5, 6, 9, 10. D is node 4. That would be 7, 8 to be solved later. So these are the equivalent nodal forces at node 2, negative 37.5. Then at node 3, which is 5, negative 163.125, and the moment, which is counterclockwise, positive 18.75. And finally, at node 5, which is 10, number 10, the nodal load is 29.25 kilonewton meter clockwise, and that's negative here. Then EI, then you have to determine 4,4. So 4,4 is, for instance, 2 here plus nothing, so that's why it's 2. 4,3, row 4, column 5, 4,5 rather. 4,5 is, we have negative 3/4 here, no 4,5 here, so negative 3/4. 4,6, 4,6 is 1. There's no 4,6 here, that's why it's 1 here. 410 is of course 0. There's no 410, so 0. Then copy negative 3/4, 1 and 0 because it is symmetric. Then this is 5,5. 5,5 is 3/8 plus 3 over 16. 3/8 plus 3 over 16 is 9 over 16. 5,6, row 5, column 6, 5, 6. So we have negative 3/4 here, and here 3/8, negative 3/4 plus 3/8 is negative 3/8. 510, so 510 is 3/8, so we have 3/8, copy negative 3/8, copy 3/8. Then 6,6, we have 2 here, and 2, and here it's 1, so 2 plus 1, it's 3. Then 610, 610 is 1/2, so that's why it's 1/2 here, so copy 1/2. Finally, 1010, 1010 is 1. So this is the global stiffness matrix for 4, 5, 6, 10. Then U4, U5, U6, U10. This corresponds to theta B, delta C, theta C, and theta E. So we can now solve this as the inverse of this matrix times this force matrix here. So we get theta B, delta C, theta C, U sub E equal to negative 462 over EI, negative 1295 over EI. Again, this is the product of the inverse of this matrix and this 4/1 force matrix. So we obtain these values, which are the same answers from the lecture part. Then having found this, let's consider AB to solve for delta A and theta A. So considering AB, the forces would be, we now consider AB as, imagine as fixed-ended A and B. Fixed-ended A and B. The fixed-end moment would be W45 L square 1 square over 12, 3.75 here counterclockwise, and 3.75 kilonewton meter here clockwise. Then the vertical fixed force is W45 times 1 divided by 2, 22.5, 22.5. So the nodal load at A or node 1 would be opposite to this friction forces. So 22.5 downward, negative 22.5. Then this is counterclockwise. So clockwise, 3.75, negative 3.75 clockwise. Don't mind F3 and F4 because we have found already theta B. Delta B, of course, is 0 because that's a support. So this corresponds to delta A, theta A, then delta B, which is 0, and theta B, which is already computed, negative 462 over EI. Then by partitioning, we only expand this part. So this matrix times this unknown displacement matrix, theta A and delta A and theta A. So 24, 12, 12, 8. By the way, for 1, 2, 3, 4, that's the stiffness of member AB. The stiffness of member AB is 12 times 2, 24, divided by 1 cube, so 24. 6 times EI1, EI2, so 12 divided by 1 square, so 12, and the rest you can verify these values on the cells. Then this matrix 24, 12, 12, 8 times this matrix delta A, theta A, then plus this matrix here 3, 4 times this known displacement 0, 0, negative 462. So negative 24 times 0 is 0. 12 times negative 462 is negative 5544. Then negative 12 times 0 is 0. 4 times negative 462 is negative 1848, equated to negative 22.5, negative 3.75, just this part here. So transpose negative 22.5 plus 5544 is 5521.5. Negative 3.75 plus 1848 is 1844.25 equals this matrix here. So therefore, we can solve delta A and theta A as the inverse of this matrix times this matrix here. So the result is delta A is 459.188 over EI, and theta A is negative 458.25 over EI. So that's it for A. Next, we consider EF. Let's compute this displacement delta F and theta F, like what we did for AB. So considering EF, this would be the stiffness of EF 12 times 1, because EI is I, over 2 cubed, so 1.5, 6 times 1 over 2 squared, that's also 1.5. Then you can generate all this for students in matrix structural analysis. Forces at E, don't mind, you just call it F9 and F10. And at F, we have negative 24 downward, 0 moment. Then EI, this is the stiffness matrix of EF, then times the displacements at E, which is 0 delta E, then theta E, we already computed this in the preceding slide, 498.75. Then the unknown displacements delta F, this is delta F and theta F. So we expand this part, negative 24, 0 equals this matrix times this displacement matrix plus this matrix times this unknown displacement matrix, delta F and theta F. So simplifying, negative 1.5 times 0 is 0, negative 1.5 times 498.75 is negative, transposed to the left, so it becomes positive. Negative 24 plus 1.5 times 498.75 is 724.125. Likewise, 0, 1.5 times 0 is 0. 1 times 498.75 is 498.75. So 0 minus 1 times 498.75 is negative 498.75 equals EI, this is the EI, times this matrix times this unknown displacement matrix. So finally, we can solve delta F and theta F as the inverse of this matrix times this force matrix here. We'll get delta E 933.5 over EI and theta E 450.75 over EI. Then finally, for E, we go back to consider B, C, D, E. Then we only B, C, D, E, the numbering would be 3, 4, 5, 6, 7, 8, 9, 10. All the displacements here are known except for delta D and theta D, which corresponds to U7 and U8. U7 and U8. So row 7 and U8. So we fill up only row 7 and row 8 and this column numberings here because the displacements of the other numbers are already found. So we set up KCD because we already have KBC before. So KCD is CD 12 times 1 over 2 cube 1.5, 6 times 1 over 2 square 1.5. So the rest you can generate these stiffnesses. Then for DE, which is the same as CD, except for the numbering, so it's the same. The numbering would be 7, 8, 9, 10 for DE. D is 7 and 8, then E is 9 and 10. C is 5 and 6, D is 7 and 8. Then we expand, we fill up this part. 7, 3, we'll have 0 stiffness because they are very far. 7, column 4, 0 also. So, while 7, 5 is negative 1.5 here, negative 1.5. 7, 6 is negative 1.5 also, that's negative 1.5. 7, 7 is 1.5 here, then another 7, 1.5 here, so 1.5 plus 1.5 is 3. 7, 8 is negative 1.5 here, while 7, 8 here is positive 1.5, so negative 1.5 plus positive 1.5 is 0. 7, 8 is negative 1.5, 7, 8 positive 1.5, that's why it's 0. 7, 9, there's no 7, 9 here, but here 7, 9 is negative 1.5. Then 7, 10, 7 and 10, we have 1.5. Then 8, 3, 0, 8, 4, 0, 8, 5. 8, 5 is 1.5, 8, 6, 8, 6 is 1, so that's why we have 1 there. 8, 7 is negative 1.5 here, while 8, 7 here is positive 1.5, so negative 1.5 plus 1.5 is 0. 8, 8, we have 2 here, and 8, 8, another 2, 2 plus 2 is 4. 8, 9, negative 8, 9. 8, 9 is negative 1.5, negative 1.5. And 8, 10 is 1, so that's why it's 1 there. So these are the corresponding displacements. Nodal forces, don't mind at 3 and 4. Then at at C, we have 90, moment is 60, then CD, because we consider CD, imagine C and D are fixed, the fixed moment would be 45 times 2 square over 12, and that would be 15 counterclockwise here, 15 clockwise on the other side, and the force upward reaction is 45 times 2 over 2, so 45 upward, 45 upward. That's why the load here is 60 clockwise minus 15 counterclockwise is 45 clockwise, but the nodal load is counterclockwise 45, so that's why we have positive 45 here. And that negative 135 is, we have 90 upward plus 45 upward, so 135 upward, but the equivalent nodal load is opposite downward, so that's why we have negative 135 downward. Then at 7, which is at D, we have 45 downward, so negative 45, and this is clockwise, so opposite, the load is opposite, counterclockwise 15, so that's positive 15. Then at E, don't mind because we already found the displacements. We are only interested of the displacement at D. So we expand row 7 therefore. So expanding row 7, we have negative 45, then 0 times 0 is 0, 0 times negative 462 is 0. Negative 1.5 times negative 1295 is positive to the left, so minus. So negative 45 minus 1.5 times 1295, which is this. Then negative 1.5 times negative 84.75, that's positive, but transposed to the left, it's minus again. So minus 1.5 times 84.75. Then 3 times U7, just leave it 3 U7 EI. Then 0 times U8, negative 1.5 times 0, so it doesn't affect. Then finally 1.5 times 498.75, that's positive, transposed to the left, so minus. So minus 1.5 times 498.75, then equals 3 U7 EI. So since we can evaluate this, divided by 3, so the value in the left side is negative 2862.75 equals 3 EI U7. So U7 is negative 2862.75 over 3 EI. And that is U7 delta D is negative 954.25 over EI. Then also we expand row 8, 15, 0 times 0, 0 times negative 462 is 0 also. 1.5 times negative 1295 is positive, negative rather, transposed to the left, so plus. So that's why you have plus 1.5 times 1295 here. 1 times negative 84.75 is negative, transposed to the left, so it becomes positive. So 1 times 84.75, so positive. Then 1 times U7, so don't, 1 times negative 84.75, negative 84.75, transposed to the left, so it becomes positive, which is this. Then plus 0 U7 plus 4 U8, so this is now 4 U8 on the right side. Then plus negative 1.5 times 0, so it's still 0. Then plus 1 times 498.75, positive 498.75, transposed to the left, so minus 1 times 498.75. Then equate to 4 U sub 8 E over EI, 4 U8 EI. Then finally we can solve U sub 8, which is theta D, and it is 385.875 over EI. So that's it for this video. It's very lengthy now. So I hope that you were able to, especially students in matrix structural analysis, you're able to follow the explanations and the solutions.